There we go. OK. So sorry. So what's a property test? Ordinary example-based tests, like the kind we're all familiar with, assert that for a particular input, your program or function produces a particular output. Property tests allow you to make a stronger assertion that for any acceptable input, your program produces an output where some property holds. A generative property testing framework will repeatedly ensure that your output property holds for every input that it generates. And while a good type system makes property testing a lot easier, we'll see today how it can be done even without a type system integration in JavaScript. Property tests share a lot in common with contract systems. They both provide runtime facilities for making assertions about the values in your program. But where contracts only run against values that end up reaching that point in the program, property testing frameworks, they will run your program or function against all acceptable inputs. So let's look at some of the assertions we can make in a property test. This first one says, for any list, regardless of the number or kind of its elements, reversing it twice gives you the input list. The second one is reversing, for any list, regardless of the number or kind of its elements again, sorting it twice will give you the same list as sorting it once. And for any number, adding 0 will give you the input number, which actually isn't true about JavaScript, but don't worry about that. As far as I'm aware, Haskell's QuickCheck was the first widely adopted property testing library for general purpose programming language. Closure Spec had a big hand in popularizing property testing, and now property testing libraries exist for most popular programming languages. Modern libraries, like PureScript StrongCheck, have added more advanced testing features, such as exhaustive and statistical tests. And state-of-the-art libraries like PureScript Jack are rethinking the way they generate their inputs so that they can provide the best possible counterexamples. So the testing library we're going to be using is called GemTest. It has built-in generators that can be used for generating subsets of the integers, characters, strings, and booleans. And that's it, I think. That's all the built-in generators. So the way we get values out of a generator is by sampling it. We call this sample function. It takes a generator and a number of values to generate, defaulting to 10. For built-in generators, one thing to know is that later values are more complex, whatever that means in the type that it's generating. So integers have larger magnitudes, and arrays are longer, and so on. So let's take a look at a test. Here's a test using Mocha and GemTest. And we're going to test a JavaScript serialization library. So this test is very simple. We're just trying to make sure that the encoder is fully deterministic in its integer serialization. And you can't see the colors very well there. That's unfortunate. So I've highlighted just the important parts. So the top one says we're sampling integers, and then we're making sure that if we encode that integer, it's the same thing as encoding it again. It will always have the same result. This other example shows a case when we have a function and its inverse, and usually when we have that, we can test round tripping through those functions. So here we're sampling integers again and ensuring that the round trip gives us the same thing that we started with. So the built-in generators, there are so few of them, they're not going to be sufficient for most use cases. So we're going to have to build generators of our own. GemTest provides some functions for creating our own generators. Elements is the first one we'll go through. Elements turns any non-empty array into a generator. So when that generator is sampled, the generator produces random entries from the given array. Constantly is just a shorthand for the single element case. So some of these functions that produce generators take other generators as input. These are combinators. ArrayOf is one of those. It takes a generator and gives us a generator of arrays. Each of the elements of those arrays are sampled from the generator that was passed in. So here in this slide, if we pass bool instead of int, we get arrays of bools. And since ArrayOf produces a generator, we can even pass the output of ArrayOf to ArrayOf, and we get arrays of arrays. So let's take a look at some more tests again. Testing the same serialization library. If we're sampling from ArrayOf, and we are asserting that when we round trip an array of anything, that the length is preserved. So other combinators are one-of, which samples at random from given generators. Shape, which generates records, and where the values of each field are sampled from the generator assigned to each of those fields. And such that, which is an interesting one. This one uses a predicate, which is the first parameter there, to filter the values generated by the given generator. But it comes with a catch. Actually, I'll skip that for now. Let's show you what this does. I'll get to it. The top example is generating only non-empty arrays. And the bottom example is generating only the even numbers, even integers. But the catch is that if the predicate that we're using rarely is true, we're going to be throwing away a lot of the values we're generating, it could be very expensive. So instead of generating values through filtering like this, we should try, when possible, to generate values through construction. So that's why we have SMap. SMap is another one of these combinators. I guess this one is parameterized, but once you pass it a function, it's a combinator, and it produces a generator that applies the function that you pass to it to every value generated by the given generator. So the top one is an example of the even integers generator that we saw before, that we were generating through filtering, done through construction instead with SMap. The one below it is odds, and it's very similar. So back in our tests, we use SMap here on the integer generator to generate only positive integers. We're SMapping math absolute value function. And where our assertion is that our serializer is encoding them as uints. But the non-empty array generator that we saw with such that can't be constructed using SMap alone. We need something more powerful for that, and that's why we have bind. Probably a lot of you, this is a LambdaConf talk, you're probably familiar with this, but I'm going to go in anyway. So bind, notice how I've aligned the arrows to make the signatures look very similar. With SMap, the function that you pass it takes a generated value and produces an alternative generated value. But with bind, the function takes a generated value and produces an alternative generator. And that generator is used to sample the values. So this is it looks like a small change, but it actually makes bind much more powerful than SMap, and in fact allows us to construct all of the other functions that we've seen up to this point using bind. So here we can now create our non-empty ArrayOf function using bind. It's a little confusing at first, but the short description is that it puts another element on the front of any array generated by the ArrayOf generator using conf. So then it'll never be empty if you always put one extra element on. Okay, so that's it for GemTest. But I wanted to go into some areas where it can be improved, because this is a very small, basic library, but there are many improvements. So my biggest issue is that all the values are generated eagerly. So before you ever make any assertion, you're already generating your entire, every value that you would ever want to make an assertion on. So if they instead use JavaScript generator functions underneath, they can generate the values only as needed. Shrinking is commonly found in other property testing libraries. It minimizes a counterexample after you find one, so that it's easier to understand the counterexample. And some other JavaScript property testing libraries have integration with the flow type checker, which is really convenient. So it automatically defines the generators for you for the types your functions operate on. And there's even academic projects looking into how a counterexample can produce a suggested resolution for limited cases. So if it just fixes your code for you, that's nice too. This is where the project we've been talking about lives on GitHub. And that's it.